Hi everyone, welcome to this session on ZGC. I'm Per Liden. I'm part of the team developing the hotspot JVM at Oracle. And by the way, I'm lead for the ZGC project. So feel free to ask questions during this talk, and we have experts standing by to answer those. And if time permits, I'll bring some of those questions up at the end of the talk. So this is the outline for this talk, and I'll start with giving you an overview of what ZGC is. We'll have a look at the design of ZGC, some performance numbers, what you need to know to get started using ZGC, and we'll end with having a look at the roadmap. Okay, so let's start with an overview of ZGC. So this is how we typically describe ZGC, and that is a scalable low latency GC. And to get a little bit better understanding of what we mean with that, we can have a look at the goals we set up when designing ZGC. So when we're talking about low latency, we refer to pause times. And the goal for ZGC is to never have a pause time above 10 milliseconds. When it comes to scalability, we are referring to that this GC should work well on basically any heap size. So whether it's very small or very large, where very large can mean multi-terabytes. And of course, it should be able to do this while maintaining the max 10 millisecond pause time. We were also ready to pay something to get the low latency and to get the scalability. We're ready to pay in terms of application throughput reduction, and we're ready to pay at most 15% compared to when using the default GC G1. Another goal we've had with ZGC is to make it easy to tune. So as you might know, many of the existing GCs have a lot of configuration options. Not that many people know exactly what all of those flags do. Java developers often spend a lot of time on tuning and tweaking those, and we sort of want to get away from that situation. We want ZGC to work nicely out of the box, and to expose the tuning options we do expose, we want them to be as easy to understand as possible. So here we see a little bit of an overview of the GC landscape. This is a list of the Oracle supported GCs and what they're optimized for. We have serial GC at the top, optimized for low memory footprint. This is something you would use in constrained environments, typically an embedded system or something similar. We have parallel GC, which is a throughput-oriented GC. Then we have G1, which is the default GC today, and that tries to offer a good balance between throughput and latency. And then we have ZGC, which is addressing that low latency part of this spectrum. Here we see an overview of ZGC from an algorithmic point of view. So perhaps the most important thing to know about ZGC is that it's a concurrent GC. That means that all the heavy lifting the GC is doing is done while Java threads continue to execute. It's a tracing GC, which means that all GCs and hotspot are tracing, and that just means that the GC will be walking the object graph on the heap to figure out what's live and what's garbage. It's compacting, so it will be moving objects around on the heap to fight fragmentation. And today it's a single generation GC, so it does not have a young and an old generation. It's region-based, which means that the heap will be divided into many smaller regions, and the GC will choose to focus its compaction efforts onto a subset of those regions, typically those that contain the most garbage. It's NUMA aware, so whenever a Java thread is allocated in an object, that object will end up in memory that is local to the CPU. And that will, of course, give you nice memory latencies. And it's using load barriers and color pointers as the sort of main techniques to achieve concurrency. A key property to understand about ZGC is that pause times do not increase with the heap or live set size. So it doesn't matter if you have a 8 megabyte heap or an 8 terabyte heap, the pause times will be unaffected by that. However, today, ZGC's pause times do increase with the root set size. And root set size is roughly equivalent to number of Java threads your application is using. So if you have a huge number of Java threads, that can affect pause times today. And I say today because, as we'll see later when I talk about the roadmap, we'll see that this will no longer be the case in the future. Okay, so I'm saying ZGC is a concurrent GC, and as you might know, other GCs have concurrent components in them. And here I'll just show you the differences. And on the left side here, we have a list of all the heavy work a GC needs to do to collect garbage, where marking and compaction is typically the two most heavy ones, but things like reference processing can be very expensive too. So if we first look at serial and parallel, no surprise, none of the work they do is concurrent. And, these are stop the world collectors by design, so no surprise. If we look at the G1 and CMS, it looks like this. So they have concurrent marking. CMS also have concurrent sweeping, but it doesn't do compaction. But you should note that both of these collectors only have concurrent marking when it comes to collecting the old generation. When they're collecting the young generation, it's still a stop the world event. And by the way, as you might know, CMS is no longer with us. That was removed in JDK 14, but it's kept here for reference. And if we look at ZGC, it looks like this. So basically everything ZGC does is concurrent except thread stack scanning. And as you can see on the slide, it says not yet. And again, this is an item I'll come back to in the roadmap section. Okay, so these are the platforms ZGC supports today. So all commonly used platforms, Linux, Windows, Mac OS on x86, and on Linux there is also support for ARM on 64-bit. This shows you a little bit of version history of ZGC. So it was initially released as an experimental feature in JDK 11. At that time, it only supported Linux on x86. And in the following releases, a lot of things have happened. New features has been added, a lot of stability improvements, performance improvements, support for all the other platforms was added, and so on. And today, with the release of JDK 15, we're very happy to announce that it's production ready. So that means, of course, that it's no longer an experimental feature. We encourage you to use this in production. And if you run into problems, Oracle will happily support you. Okay, so let's have a look at the design of ZGC. And you don't necessarily need to know a whole lot about how ZGC works to use it, of course, but it could be useful to know a thing or two, and it might help you tune it and better understand how to interpret GC logs. So this shows you what the GC cycle looks like in ZGC and the phases it will go through. And I'll just quickly walk you through this and say a few words about what's going on in each of these phases. So a cycle starts out with the mark start pause. Here we do scan thread stacks, and we scan thread stacks to find roots, and roots are basically pointers pointing into the Java heap. This will give us the starting point for marking. And then we continue again in concurrent mode. So Java threads now continue to execute while we, using those roots we just found, mark through the whole heap by walking the object graph. And the objects we find will be marked live, and those we don't will implicitly be considered to be garbage. We then come to the mark end pause. This is just a synchronization point to end the marking phase. And then we continue in concurrent mode again. And here we do a couple of things. We first do reference processing, so taking care of soft, weak, and phantom references and finalization. We do class unloading, so If there are class loaders and its classes that are no longer in use, then resources occupied by those will be freed. And finally, we do relocation set selection. And relocation set selection means that using the liveness information we have from the marking phase, we can now make a good decision on what parts of the heap we want to compact. Then we continue into the relocate start pause. Again, we scan thread stacks. This time we want to find routes pointing into the relocation set. In other words, routes pointing to objects that are about to be moved, and we want to treat them especially. Then we continue in concurrent mode again, and this is where we do the heavy work of actually compacting the heap. And that concludes the GC cycle. And I just want to point out here then that we do have 3 short pauses for each GC cycle, and it's these pauses that we're saying are never going to be longer than 10 milliseconds. So colored pointers is a sort of a core design concept in ZGC. It basically means that we, in 64-bit pointers, in object references, in hotspot, not all of the bits there are typically used because we're not using all of the address space. So we're taking advantage of that and using some of those unused bits to store metadata. This metadata we call colors, and this metadata tells us something about the object this reference is pointing to. So for example, it could mean that this object has been marked, or it has been relocated, or it needs to be, the object has moved, but we now need to figure out where it moved to. So color pointers go sort of hand in hand with our load barriers. And in general, a GC barrier is just a small piece of code that is injected by the JIT in strategic places. In ZGC's case, that strategic place is when we're loading an object reference from the heap, or when the application is loading an object reference from the heap. The purpose of the load barrier is to check if the reference has a bad color or not. If the color is bad, then that means some kind of action needs to be taken. That action could mean that the object here needs to be marked, or it needs to be relocated, and so on. Once that action sort of has been taken care of, we also heal the reference. So we're writing back the correct address and correct color back to the place where it was loaded from, so that the next time you load this reference, the load barrier will have nothing to do, and no action needs to be taken. And so a little example here, we have an instance of person. The person class has a name, age, and height field, where the name here is an object reference pointing to a string. And in this example, we are saying n equals person.name. So we're loading something, the object reference in the field name, and storing that into the local variable n. So this is a typical example of where we're loading an object reference from the heap. So the JIT will go ahead and insert a load barrier right here. Then we have a few more examples. We're assigning, or p equals n, where we're assigning one local to another. We're not loading something from the heap, so no load barrier will be needed there. Next, we call the isEmpty method. Again, not loading something from the heap, so no barrier needed. And finally, in this example, we have age equals person.age. That is actually loading something from the heap, the age field. But that's an int and not an object reference, so again, no load barrier will be needed. So if we zoom in a bit on the load barrier here and expand that, it will conceptually look like this. So the reference we just loaded into n is tested against something called a bad bit mask. This bad bit mask is a global state telling us what colors we should be considering to be bad at this time. Exactly what colors are considered good or bad at any given time depends on which GC phase we're currently in. But if this if statement here says that, yeah, this is a bad color, then we take a slow path. In other words, call into the VM and take whatever action needs to be taken. Again, that could mean that this object needs to be marked, or it needs to be relocated, or it has already been relocated and we now just need to figure out where it moved to. And the slow path will also yield the reference. So writing back the correct address and correct color for this reference. And if we take this one step further and look at what the C2 JIT compiler in hotspot will generate, it looks like this. So we have the move instruction that corresponds to the actual load. And then we have the two instructions here in red, which is the actual load barrier. A test on a branch, a test for a bad color, and a jump into a slow path in case we found one. So that's it. The whole load barrier is just two instructions. And on today's hardware, this is typically a well-predicted branch. Okay, so let's have a look at some performance numbers. So here we have Spec JBB 2015. This benchmark produces two scores. One is called max JOPS. That's a throughput score. The other score is critical JOPS, and that's a latency score. In this example, we're using a 128 gig heap. And if we look at the throughput score here in the green bars, we see that the G1 collector is slightly ahead by a few percent. On the other hand, if we look at the latency score in yellow, we see that ZGC is well ahead. And that's, of course, thanks to its low pause times. And speaking about pause times, this is what it looks like for the same benchmark. So in this case, or in this graph now, lower is better. We have milliseconds on the y-axis from 0 to 500. And if we look at G1, we see that it has an average pause time of around 150 milliseconds, a max pause time of something like 470 milliseconds. And if we look at ZGC, I haven't actually removed the bars here. The pause times are so small that they don't register on this scale. So if I change the scale, instead of having 0 to 500, we go to 0 to 5 milliseconds. In other words, zooming in by a factor of 100, it looks like this. So on average, ZGC on this workload has a pause time of around half a millisecond, and max pause time is just above 1 millisecond. So as you can see, a pretty significant difference here in pause times, and yet we didn't pay that much in terms of throughput reduction. So next we have another benchmark. This is called the Big RAM tester. This is basically a GC stress test that causes a lot of heap fragmentation. So it means the GC will have a lot of work to do to compact the heap. And as we can see, the story here is very similar. G1 in this case has an average pause time around 250 milliseconds, max around 470. And again, I need to change the scale and zoom in by a factor of 100 to see the ZGC pause times. And we can see that on average, the ZGC pause time is roughly 0.2 milliseconds and max slightly below 1 millisecond. So I sort of hope you can translate what this could mean for your workload. I mean, if you have a latency sensitive workload and you're today struggling with meeting response time requirements because of poor GC pause times, then ZGC could be a game changer for your workload. Okay, so a few words on using ZGC. First of all, I'd recommend everyone to use the latest JDK version. A lot of improvements is going into each JDK release. This is especially true for ZGC. Those improvements will continue to come, and especially in case of ZGC, a lot of things have happened since JDK 11. So if you're looking for the best performance, best latency, newest features, and so on, then I highly recommend you to stick to the latest version. So to enable ZGC, there's this flag, use ZGC, similar to how you enable other GCs. If you happen to be on a JDK release 14 or earlier, in other words, when ZGC was still an experimental feature, then you also need to supply the unlock experimental VM options flag to start ZGC. Then we come to tuning. And as I mentioned in the beginning here, we've been working hard to make ZGC easy to tune. And the main tuning option you want to have a look at is setting the max heap size. So what numbers should you pick? Well, of course, you first of all need to have a heap size that is large enough to hold the application's live set. But you also need to have a certain amount of headroom in your heap. And that headroom will basically dictate, or the size of that headroom will basically dictate how often you need to do a GC. But you should also remember that this is a concurrent GC, so that headroom is also there to allow allocations to be serviced while the GC is running. In general, the more memory you give to ZGC, the better, but you obviously don't want to waste memory, so it's all about finding a good balance between memory usage and how often the GC needs to run. The next tuning option that you might want to have a look at is setting number of concurrent GC threads. ZGC has heuristics to pick a good number for you. This usually works well, but there are workloads where you might want to adjust this. So this option basically says how much CPU time you're willing to give to the GC. And if you pick a number here that is too high, then there's a risk that the GC will steal too much CPU time from the application. And if this number is too low, then there's a risk that the GC won't be able to keep up, collecting garbage at the same rate as it is created. So just to recap here, there's one option which basically says how much memory you want to give to the GC, and another option which says how much CPU time you're willing to give to the GC. And that's pretty much it. There are a few other options too, but these are by far the two most important ones to get right. If we look at GC logging, I would recommend you to use one of these two options, either xlog GC, which will give you basic logging, basically one line of output per GC cycle, very high level information. Or if you want more detailed logging, use the xlog GC star option. This is useful when tuning or you want to solve a problem or get more information on what's going on. This is an example of what basic logging looks like. So one line of output per GC cycle. Again, very high level information. Here you can see why the GC started, what the heap usage looked like before and after the GC cycle. This is what the GC log looks like when you have the detailed logging enabled, and you'll get this information per GC cycle. There's a lot here. I won't go through it all, just highlight a few things. Here you have the timing information for the various phases. So in this case, we can see that the mark start pause took 0.4 or so milliseconds. Down here we have the sort of a view of how the heap has evolved throughout the GC cycle. So you can see how much was used when the GC cycle started, how much was live once the marking phase ended, how much was garbage, and eventually how much garbage was reclaimed. So when you have the detailed logging enabled, you will also see this table with a bunch of GC statistics counters. And this, I'm only showing you the top half of the table. The 4 columns here represent 4 different time windows. So what has happened in the last 10 seconds, 10 minutes, 10 hours, and total since the JVM started. And if we pick a few examples here we'll have we see the allocation rate for the application. So at some point, we can see since the JVM started, at some point, this application allocated something like 13 gigabytes per second but on average, it has allocated about 2.2 gigs per second. Down here, we have pause time statistics. So again, if we look at the total column, we have sort of a summary of all the pauses that has happened so far. We can see that the average pause time is roughly 0.5 millisecond, and the max pause time here seems to be a relocate start pause at 1.17 milliseconds. Okay, so a few words about the roadmap. And of course, we have a number of items on that roadmap. I'm just going to bring up the two most interesting ones here, or two most important ones for most users, and that is sub-millisecond max pause times and generational ZGC. So if we start with sub-millisecond max pause times, you might remember this slide from the beginning of the talk where I said these were our goals. At this point, we've basically met all these goals, and pause times are typically a lot lower than 10 milliseconds. So it's now time to step it up a bit and adjusting these goals. And our current goal is to never have a max pause time longer than 1 millisecond, sorry. Of course, while still maintaining the scalability and so on. So I showed you this also, and I said that today ZGC is doing everything concurrent except the thread stack scanning, and that's still done in a pause, and that's what we plan to address. So that means this will no longer be true. So GC pause times will no longer increase with the root set size, which translates into that you can have any number of Java threads you want in your application that will have zero impact on GC pause times. So if you're interested in this work and want to follow its progress, you can have a look at JEP 376, ZGC concurrent thread stack processing. Here are some preliminary results from our current patches. Again, we're using spec JBB 2015 here. However, this time we're using a much larger machine and a much bigger heap. So we're using a 3 terabyte heap, more than 200 hyperthreads on this machine. And this benchmark will start up more than 2,000 threads when executed on this system. So again, I'm showing you the pause times here. So lower is better. And we see the numbers for ZGC today. Average pause times look good, an average of 1 millisecond roughly. And we have a max pause time of around 7 milliseconds, which is still pretty good. We're below our initial target of 10 milliseconds, but it's not good enough if you want to reach sub-millisecond max pause times. So with concurrent thread stack scanning, in other words, JEP 376, it looks like this. So that's a pretty significant difference. We're now down to average pause times of around 100 microseconds, so 0.1 millisecond, and max pause time of around 500 microseconds, so 0.5 milliseconds. We are very excited about this, and we hope that once we reach this and have this integrated in a JDK release, we hope that we sort of finally can say that GC pause times is problematic GC pause times is a thing of the past. Okay, so the next item I wanted to talk about was generational ZGC. So as I mentioned also in the beginning, today's ZGC has a single generation. So it doesn't divide the heap into a young and an old generation. And we plan to change that. Once you have a young and an old generation, you can of course exploit the fact that most objects are short-lived. And the benefits of doing this will be that ZGC will be able to withstand higher allocation rates, basically collect garbage faster. It means we will need less headroom in the heap. And also we will use less CPU to collect garbage. So basically, number of CPU cycles per collected byte will be less. This is still work in progress, so I hope, or I don't have any numbers to show you here today, but stay tuned. Okay, so if you're interested in more information on ZGC, I would recommend you to head over to the OpenJDK wiki, which has a ZGC subpage. There you'll find information on how to configure and tune ZGC. You'll find links to blog posts, other talks, videos, mailing lists, and source code repositories, and so on. This is sort of the main source of information for ZGC. We also have the hotspot GC tuning guide, which is part of the normal Java documentation. And of course, there is also a section on ZGC and information on how to tune it. I have my own blog where I from time to time write about ZGC. So if you're interested in ZGC development and want to see what's happening in ZGC land, then head over to malloc.se. And before we go to questions, I just want to encourage everyone to go download JDK 15. It will be an awesome release. ZGC is production ready. Please try it out. You know, let us know how ZGC works on your workload. And with that, I think we're ready to take some questions. Let's see here. Okay, so first question. Many of our applications don't need huge heaps. Is ZGC still something to consider? And the simple answer is yes, absolutely. So ZGC works really well on basically any heap size. It's definitely not a GC only targeting very large heaps. It's a GC primarily targeting use cases where you want low latency. And it just so happens that it works really nicely on huge heaps too. And to be, I think I mentioned this already perhaps, but to be very specific, today ZGC can handle heaps ranging from 8 megabytes up to 16 terabytes. Okay, so next question. Okay, so I sometimes see allocation stall reported in the GC log. What is that? So if you see an allocation stall in the GC log, that's a sign that the GC is unable to keep up with the current allocation rate. And it's a sort of a bad situation in the sense that allocating threads had to wait before they could allocate, and you want to get away from that basically. And it a little bit depends on the situation here, but let's say you have a back-to-back GCs all the time, and you also see a lot of allocation stalls all the time. That's a typical sign that you have a too small headroom in your heap. So first you want to try to increase the max heap size to give the GC more memory to work with. If that doesn't work, or you can't expand max heap size, let's say you're using everything there is in the machine, then the next option is to adjust the number of concurrent GC threads to give this GC more CPU time so that it will essentially become faster. There is a sort of another sort of case where you might see this, and let's say you only see allocation stores very occasionally. Most of the time things work nicely, and once in a while you see an allocation stall. Perhaps it's when the workload sort of spikes and you have a huge increase in the allocation rate. At that time, you might want to look at the softmax heap size option. And with the softmax heap size option, if you set that to something lower than the max heap size, you will basically, in a way, tell ZGC to collect garbage more aggressively, and you can sort of give yourself more headroom without necessarily extending the max heap size. And finally, once ZGC has generations, running into allocation stalls should hopefully be, or the risk of doing that should be a lot lower. Okay, so next question. Okay, so question is, will ZGC ever shrink the heap? And the answer is yes, sort of in the sense that if ZGC detects that some of the heap regions has been unused for a certain amount of time, by default that time is 5 minutes. If it detects that, then ZGC will go ahead and uncommit that memory, in other words, returning it to the operating system. And as soon as it sort of detects that, oh, all of a sudden I need this memory again, it will be again committed. But sort of it will return it if it's unused. And as said, the default is 5 minutes. There is an option called set uncommit delay, where you can, change this policy, make it uncommit more aggressively or less aggressively. The only thing to keep in mind is that you shouldn't set this too low, because then ZGC will just uncommit memory and immediately after it detects that it needs that memory again, it will commit it back in. So, you haven't gained anything, you just wasted a bunch of CPU cycles. So next question. What's the overhead of the load barrier? So, of course, that since we're generating load barriers when you're loading an object reference from the heap, it very much depends on what the workload looks like, how frequent are loads versus stores and other operations. But in general, the measurements we've done indicate that the overhead is somewhere between 0 and 5%. As I mentioned before, the branch there on modern hardware, that branch is typically very well predicted. And the sort of good versus bad ratio when you have a load barrier, the number of times or the ratio where you have to go into the slow path is usually 1 in a million. So 1 load in a million loads needs to sort of go into a slow path and take some kind of action. Okay, do we have more questions? When should I not use ZGC? So when the only thing you care about is throughput, you have no response time requirements at all. You only care that this program executes from A to B as fast as possible. Maybe it's a batch job or whatever. Then, if it's a raw throughput oriented load, then parallel GC is probably the GC you want to look at. But, as soon as you care a little bit about pause times, and especially if you have large heaps where stop the world GCs tend to sort of scale linearly with the heap size in terms of their pause times scale linearly, then looking at ZGC is a good option. So next question is, when will generational ZGC be available? And as always, I don't have an answer for that. We're working on it as hard as we can. And as soon as we are happy with the functionality, stability, and performance, we will try to ship that in a future JDK. So with that, I think I'm running out of time, and I say thank you for attending this session. Up next, we have 2 sessions. One is titled "This Ain't Your Parents' Java." The other one is the path towards Spring Boot native applications on Graal VM. So please head over to the website for the event agenda. You see the URL here on the screen, and on there you can click the join button to join either of the upcoming sessions. Thank you.